All right, today we are going on a mathematical quest. We're going to take on an integral that, let's be honest, looks pretty intimidating. But it's an awesome challenge, and we're going to break it all down together, one step at a time.
You know the feeling, right? You look at a problem, it's filled with all these wild symbols, and you're just thinking, where do I even start? Well, today, we're not just going to look at one of those problems, we're going to solve it.
So, here it is. Meet our mathematical monster. Now, I know there's a lot of stuff on this slide, but just ignore all that for a second and look at the very first line with me. That's our target. The integral of e to the negative beta x times this funky-looking function called brex. Our entire goal here is to find the answer to that integral, which we're just going to call omega. To start any quest, you need the right tools. And for us, the very first tool is figuring out what this uber thing even is. It is literally the key that's going to unlock this whole problem for us.
Okay, so brex is not your everyday function from algebra class. It's a special one, called a Kelvin function. And here's the part that's absolutely crucial for us, its definition. Brex is just the real part of this other, much more complicated-looking expression. We don't even have to solve that new integral, we just have to use its definition like a key.
So here's the first big move. We take that entire integral definition for brex, and we literally just plug it straight back into our main equation for omega. And yeah, I know what you're thinking. It turns our single integral into a double integral, which looks way scarier, but trust me, this is a good thing. It's actually revealed a hidden structure that we can now attack. Now that we've reframed the problem, it's time to pull out our next tool. And this one is a huge shortcut. It's a powerhouse that mathematicians love for simplifying really tough integrals. Let's talk about the Laplace transform.
You can think of the Laplace transform as a kind of cheat sheet for certain problems. See, our inner integral, the one with an exponential multiplied by a cosine, it perfectly matches a known pattern. The transform gives us the answer right away, which lets us skip a ton of manual work. It's fantastic.
And here's where the magic happens. Just follow along on the slide. By using that Laplace formula on our inner integral, the dx part, that whole chunk of the problem just collapses. It turns into the simple fraction you see on the next line. And just like that, our scary double integral is back to being a single one, and it's looking a whole lot less intimidating.
We've made some serious progress, but we're not at the finish lines just yet. The integral we have now is still a bit of a beast. This next part is all about strategy. It's about using a series of really clever substitutions to find our way through the maze.
So, after applying that Laplace transform and cleaning up the algebra a little bit, this is what we're looking at. It's definitely simpler, but see that little I in the denominator? That's our clue that we're still playing with complex numbers, and we've got a few more smart moves to make before we get to the answer.
Okay, so here's our roadmap for the final push. We're going to simplify things a bit, use a neat symmetry trick to adjust our limits, and then we're going to bring out a classic calculus technique, the tangent substitution. That's going to get us so close to a standard form that one last little substitution can finally solve.
All right, time for a pro move in the world of calculus, the tangent substitution. Take a look at the integral with the sine squared term. Anytime you see something like that, a little light bulb should go off. By creating a new variable t and setting it equal to the tangent of theta, we can swap out all those trig functions for simpler algebraic terms.
And would you look at the result? No more sines and cosines. It's all just t's now. Now, it might not look super friendly just yet, but what we've done is fundamentally change the nature of the problem into something that has a lot more structure and is, believe it or not, way easier to solve.
We are on the final stretch now. After all that decoding and transforming and substituting, the summit is right there. It is finally time to reveal the solution we've been fighting for.
So the last move you see here involves one more substitution, which turns this into a standard arctangent integral. Solving that gives us this complex expression, and now all we have to do is what we set out to do from the very beginning, find the real part of this final result. That takes some careful algebra to isolate, and that gets us our answer.
And here it is, the solution. All of that complexity, all those steps, they all boil down to this one kind of beautiful, elegant expression. The value of our omega is beta squared plus the square root of beta to the fourth plus 1, all of that divided by 2 times beta to the fourth plus 1.
You know, this quote just nails the whole spirit of our journey today, doesn't it? We started with something that looked impossibly complicated, and by just applying the right tools and the right strategies, we broke it down piece by piece until it became simple.
And that is the real beauty of mathematics.
It really makes you wonder, right? What other problems that seem impossible are just sitting out there, waiting for the right approach to unlock a surprisingly simple and elegant truth. Thanks so much for joining me on this mathematical quest.